All right, so it says a 24 volt, 1 horsepower DC motor is 75% efficient, requires 1,119 watts. How much power will a 12 volt, 2 horsepower DC electric motor that is 80% efficient require? All right, remember that you do need to remember to know they're not going to give it to you the equation for efficiency. Efficiency is equal to the output over the input, and this is input power and output power. All right, so that being said, we have two scenarios. We have scenario one right here. So it says a 24 volt, 1 horsepower motor, 75% efficient, and requires, meaning the power it takes to run the motor is 1,119 watts. Okay, so the idea is what you need to do in this problem is recognize all that information is extra information, has nothing to do with the second motor. Right, it gave you everything. You have every single thing here, right? We know that 1 watt is 740, I'm sorry, 1 horsepower is 746 watts. Everything is given here, right? We have the equation efficiency, so we know that 0.75 equals our output. What's our output? Our output is 746 divided by 1119. Guess what 746 divided by 1119 is? It's going to be 0.75, right? So, and we do see here, hey, look, our input is always going to be larger than our output, right? Because a motor is going to have some losses somewhere and some loss of efficiency. Okay, so over here we have 2 horsepower. So the first thing we need to do is convert our electrical or mechanical power, because this shaft is turning with 2 horsepower, convert it to electrical power. So let's go ahead and do that. So 2 times 746 is 1,492 watts. All right, so now we have that. We have our efficiency. All we have to do is plug it in to our equation. So we know that 0.8, I'm just going to go ahead and convert that percentage to a decimal, is equal to, this is our motor's output. This is how much power the shaft turns with, how much output I get, right? So that's going to be on the top. And we need to find out how much power it's going to take to run this motor, right? Remember this part right here, the battery and the wires and the current going through into the motor is the power it's required to run the motor. And that's what we don't know, right? So that's going to be what we're solving for. After you do these problems enough times, at the end of the day, whenever you do get your output power, you're always just going to divide it by the efficiency. But that's because of this algebraic process that we're about to show you. But every single time, take your output power, divide it by the efficiency. So we're going to solve for our input, or I. So I'm going to multiply both sides by I. I divided by I is 1. Anything divided by itself is 1. 492. 1492. And that's in watts. Then we have 0.8 times I. Now we need to get I by itself. Divide by 0.8. Divide by 0.8. Here's our output getting divided by our efficiency. And that's going to come out to be 1,865 watts of power it takes for this battery and the current, so this voltage and current, this power to run this motor, right? We see this number is larger than our output, and that's always going to be the case.